In this session, we are going to talk about 11th Physics, chapter number 4, Laws of Motion, part 5. First point is coefficient of restitution, E. For collision of two objects, the negative ratio of relative velocity of separation to relative velocity of approach is defined as the coefficient of restitution E. Next point is one-dimensional or head-on collision. A collision is said to be head-on if the colliding objects move along the same straight line before and after the collision. Here we use as u1, u2, v1, v2 as symbols. Consider such a head-on collision of two bodies of masses m1 and m2 with respective initial velocities. As the collision is head-on, the colliding masses are along the same line before and after the collision. Hence, vector treatment is not necessary. Relative velocity of approach is then ua is equal to u2 minus u1. Let v1 and v2 be their respective velocities after the collision. The relative velocity of receding or separation is then vs is equal to v2 minus v1. Therefore, coefficient of restitution E is equal to minus vx upon ua is equal to minus v2 minus v1 upon u1 minus u2 is equal to v1 minus u2 upon u1 minus u2. Therefore, E is equal to relative velocity of separation divided by relative velocity of approach as equation 4.1. For a perfectly inelastic collision, the colliding bodies move jointly after the collision, that is v2 is equal to v1 or v2 minus v1 is equal to 0. Hence, for perfectly inelastic collision, E is equal to 0. In other words, if E is equal to 0, the head-on collision is perfectly. Next point is coefficient of restitution during a head-on elastic collision. Consider the collision described above to be elastic according to the principle of conservation of linear momentum. Total initial momentum is equal to total final momentum. That is, m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2 as equation 4.2. That is, m1 in bracket u1 minus v1 is equal to m2 in bracket v2 minus u2 as equation 4.3. As the collision is elastic, total kinetic energy of the system is also conserved. That is, 1 half m1 u1 square plus 1 half m2 u2 square is equal to 1 half m1 v1 square plus 1 half m2 v2 square as equation 4.4. That is, m1 in bracket u1 square minus v1 square is equal to m2 in bracket v2 square minus u2 square. That is, m1 in first bracket u1 plus v1 into second bracket u1 minus v1 is equal to m2 in first bracket v2 plus u2 into second bracket v2 minus u2 as equation 4.5. Dividing equation 4.5 by equation 4.3, we get u1 plus v1 is equal to v2 plus u2 as equation 4.6. That is, u2 minus v1 is equal to v1 minus v2. For an elastic collision, E is equal to minus vx upon ua, which is equal to minus v2 minus v1 upon u1 minus u2 is equal to v1 minus u2 upon u1 minus u2 is equal to 1 as equation 4.7. Thus, for an elastic collision, coefficient of restitution E is equal to 1. For a perfectly inelastic collision, E is equal to 0 by definition. Thus, for any collision, the coefficient of restitution lies between 1 and 0. Above expressions 4.1 and 4.7 equations are general. While substituting the values of u1, u2, v1, v2, their algebraic values must be used in actual calculations. For example, referring to the figure 4.3a, b and c, equation 4.1 gives E is equal to minus Vx upon Ua. Here, Ua is equal to U1 minus U2 and U1 is greater than U2 and Vx is equal to V1 plus V2 since the objects are in opposite directions. Using this equation 4.2 we get m1 into u1 plus m2 into u2 is equal to m1 v1 plus m2 in bracket u1 plus v1 minus u2. Therefore, v1 is equal to m1 minus m2 into u1 plus twice of m2 into u2 whole divided by m1 plus m2 as equation 4.8. Subscripts 1 and 2 were arbitrarily chosen. Thus, just interchanging 1 and 2 gives u2 as u2 is equal to m2 minus m1 into u1 plus twice of m2 u2 whole divided by m1 plus m2 as equation 4.9. Equation 4.9 can also be obtained by substituting the values from equation 4.8 in equation 4.6. Next one is particular cases. First, if the bodies are of equal masses or identical, m1 is equal to m2, equations 4.8 and 4.9 gives u1 is equal to u2 and v2 is equal to u1. Thus, the bodies just exchange their velocities. Second, if colliding body is much heavier and struck the body initially at rest, that is m1 is greater than m2 and u2 is equal to 0. We can use m1 plus or minus m2 is equal to m1 and m1 divided by m1 plus m2 is equal to 0. That is v1 is equal to u1 and v2 is equal to twice of u1. That is, the massive striking body is practically unaffected and the tiny body which is struck travels with the double speed of the massive striking body. Second, the body which is struck is much heavier than the colliding body and is initially at rest, that is m1 is less than m2 and u2 is equal to 0. Using similar approximations, we get v1 is equal to minus u1, that is the tiny or lighter object rebounds with same speed while the massive object is unaffected. This is a good as dropping an elastic object on hard surface of the earth. Thank you.